Hey there, this is Lucius Laframboise from ENG Suite, and today we're going to finish up our ANOVA post hoc testing by talking about Duncan's multiple range test. So we've covered this a lot, but I just want to drive this home. We use ANOVA post hoc testing when our one-way ANOVA shows that one or more of our treatment levels has a significant effect, and we need to perform further testing to determine which treatments are significant. So using Duncan's multiple range test, we're going to actually group the treatments based on significance. So this is going to be a lot like our two-key pairwise, where it's going to give us groupings rather than confidence intervals or hypothesis testing. So how do we read a DMRT table? This is exactly the table that we are going to get from QE Suite. So QE Suite provides this table, and it's what we're going to calculate later in the video. And this is using the same exact data that we've already been using. And if you remember from our two-key pairwise, A, B, B, B for 1, 3, 2, 4, those are the exact groups we got last time. So we're looking good already. Okay, so the table is divided into rows for each treatment. You'll notice these aren't necessarily in treatment 1, 2, 3, 4 order as they're put into the function. That's because, again, they are sorted by the mean in decreasing order. And we're going to use that grouping column to determine which groups have significant differences. So if they share a group letter, that means they are not significantly different. For example, treatment 1 does not share group A with anything. So treatment 1 is significantly different from all other treatments. But treatment 3 shares group B with 2 and 4. Therefore, 3 is not significantly different from 2 or 4, and because 2 and 4 are both in B, 2 and 4 are not significantly different from each other as well. So the math behind DMRT. This one's actually quite a bit simpler, but it requires some outside resources. So to calculate this RP value, we first need the RP crit. And the RP crit is the RP critical value from the Duncan table. So that's a big table of values, depends on treatment orders and some things. We're not going to worry about that too much right now because we're actually going to provide that for you in the Excel workbook we're working on. Don't worry about that. Link in the description if you want to see the table though. Okay, so then it's RP crit times this SX, which equals the square root of the mean squared error over the number of treatment groups. Okay, so mean squared error, again, that comes from your ANOVA table. We're going to be using QE Suite to generate that with QE.ANOVA one-way. So make sure you get your free trial started here. Link in the description that shows you how to get started with that in just a minute or so. And we'll show you how to do that when we get into the math as well. So our D value, that is just X bar, so the mean of the treatment group minus the RP value of the treatment group, okay? So remember, RP value is a little bit different for each of these because RP crit is going to be different based on the order of the treatments. And then grouping, so here's just a quick description of how the grouping goes. First, we'll order treatments by mean and descending order. So this is new data we're pretending to use here, where these are in descending order, 1, 2, 3, 4. Starting with the first treatment, we compare it with all subsequent treatments in descending mean order, and we step through. So first, we go 1 to 2, 1 to 3, 1 to 4. Then we step to the next, 2 to 3, 2 to 4. Step to the next, 3 to 4. And if the mean of a subsequent group is greater than the current group's D value, then they're grouped together into group I. Okay, that'll make a little bit more sense. But for now, that's the math. Super easy. Like I said, we just need some outside resources. So let's get into Excel and actually do this by hand. Okay, here we are in Excel, and this entire workbook is available for you to download. Link in the description. Go ahead and download that. Now, remember I said you need QE Suite for this. So go ahead, watch this video here to get started with your free trial. Otherwise, if you download this workbook, it will automatically suggest that you install it because it has the QE Suite functions in it. So make sure you go ahead and follow the instructions and install it so that you can work along with me. So yours is actually going to have all of the math already input. So if you want to follow along, go ahead and delete that. That way you can follow along. So the first thing that we're going to do is start in this unsorted DMRT table. And we're going to do what we love to do, which is transpose our treatments. Awesome. Now we need to get our treatment means, and we're going to use average of filter, and we're going to filter the entire array of values if the array of treatments F4 to absolute reference equals our treatment name, and I forgot to absolute reference, so I'll just do that. Enter. Yes, we accept, and then double click to drop down. Awesome. We are already well on our way. So now what we can do is we can say sort by our treatments array by mean in descending order, which is -1. There we go. We have them done. Okay, so now what we need to do is we need to get our RP critical value. Okay, so our RP crit for each of these is going to be found in this based on degrees of freedom and treatment. And so what we need here is our degrees of freedom for the error term in our ANOVA. So we actually need to run our QE suite ANOVA. So equals QE.ANOVA one way. Select all of our treatments and measurements, and there we go. So here is our degrees of freedom error. So let's do this. We'll say index, and we'll take this whole, oops, can't really see it, take this whole array that includes all of the values in the DMRT table and our row number. So if we read this table here, our row is our degrees of freedom, and it starts at 1 and index is 1 based, so we can take the error, and we're good there. Now we need to get our column, which is the number of treatments. So number of treatments, our numbered treatment, not number of treatments. This is our first treatment. So what we need to do is, instead of actually starting with 1, we need to start with the high number. So this is actually treatment 1, 2, 3, 4. Okay, so how do we get 4? Well, something interesting is it's 1 based. So we need to actually start with 2 when we get to 2. So, well, let's try this. Let's take and say count all, and let's take all of these. Okay, so now we have 1, 2, 3, 4. So we're starting at 4. 1, 2, 3, 4. But that gives us 5. We want 4, and then when we drop down, we want to get 3 and then 2. So what we can do is do count A, and instead take, open our parentheses, and we'll take that, and let's absolute reference that, colon, G2 again, and make sure we absolute reference that. It took it away when I did the colon. Okay, and now we hit enter. That gives us 3.235. We drag it down, and we need to absolute reference some stuff. So absolute reference our error, and then we need to absolute reference our count all. Okay, there we go. Drop this down, and we know that treatment 4 is going to need a 0, so we'll just put 0. So the lowest one always get a 0 for RP. Okay, so now that we have the RP critical, we need to multiply that by SX, which, if you remember, is going to be the square root of our mean squared error, so in our ANOVA table, divided by our NT, number of treatment levels. So let's absolute reference both of these. Do that, equals, awesome. Cancel that. And now we get to just drag that down, and we have our RP values. Okay, awesome. So now what we're going to want to do is calculate our D values. And D is not that much harder. In fact, it's quite a bit easier. We're going to say filter, and we're going to take our mean array based on whether or not our treatment array equals the treatment name. And again, I always do this. We need to absolute reference everything. And if we do that, that will give us our mean minus our RP. Enter. There we go. We have a D. And now we are ready to group. Okay, so if you remember our grouping procedure, we're going to step through all of these and compare them. So we know that treatment 1 is part of group A. That's just a given. Is treatment 3 part of group A? Well, is our mean of that group larger than our D. So if we look at our mean, 3, is 3 greater than 3.8? No, it is not. So it is not part of group A. And we know that since they are in descending order, nothing below is going to be part of group A. So we can move on. Now we're on group B. We know treatment 3 is part of group B. Is treatment 2? Well, we take a look. Our treatment 2 mean is 3. Is that greater than 0.7, our D value? Yes, it is. So that is part of group B. Now let's pop down to treatment 4. 1.2, is that greater than 0.7? Absolutely it is. B. Okay, now we can stop there. Now if we wanted, we could look at group C, but we know since all of the rest of them are in group B, there is no unique scenario. There's no scenario where group C could be unique from group B. Therefore, we know that group C doesn't exist. It's really just a subset of group B and does not matter because it's not taking into account everything. So there we go. We finished our grouping. Let's double check with QE Suite equals QE dot, and then we're going to use Duncan Multiple Range, select our treatments, enter, and there we go. Treatment 1, everything looks absolutely perfect. Okay. Just like we did with the Tukey, what happens if we have a group that overlaps a little bit? So like in this example, again, we're going to switch that out to a 3 and see what happens. Well, in this case, we did not see an overlapping in the groupings like we did last time. So let's try 3.5. No overlap in grouping again, because as we see, our D is actually still pretty high. Let's pop this one up to 3.5 and still none. Let's try this up to 4. Okay, we had a huge shift. So as you can see, slight changes can do this, and we can manually go through this grouping. You know what? Let's do it. Let's do it together. Why not? This is a complicated grouping. It'll really show off some cool grouping logic. Okay, group A. We know treatment 1 is part of group A. So is treatment, this is 3. Yep, is treatment 3 part of group A? Well, is 4 greater than 3.93? Yes, it is. Okay, A. What about treatment 2? Is 3? No, it is not. We know treatment 4 is not. Okay, we know that it's going to be, treatment 3 is going to be part of group B. Just depends whether or not that's a significant group. Okay, treatment 2. Is that part of group B? We take a look. Treatment 2, the mean is 3, and our D value for treatment 3 is 1.4079. Well, 3 is greater than 1.4, so it's part of group B. What about treatment 4, 1.2? No, it is not. Okay, treatment 2, we know that's part of group C, but is treatment 4 part of group C? Well, let's take a look here. Treatment 4, 1.2, that is greater than 0.52. So it is part of treatment group C. Okay, but do we have any redundant groups? Well, A is good. A will always take precedent. The higher one, the group of the higher mean always takes precedent over the lowers because we never analyze backwards. We only analyze forwards. So in here, let's take a look at B. Well, B includes treatment 3 and treatment 2. Treatment 3 is part of group A, but treatment 2 is not part of group A, which means group B is a unique grouping, so therefore group B will continue to exist. And the same goes with group C. Group C contains treatment 2, which is part of group B, but treatment 4 is not part of group B, therefore C is a distinct group. So again, grouping logic, just take your time with it, or just run it through QE Suite and it handles all the grouping for you. Anyway, thank you so much for watching. Have a great day, and please do something awesome.